Hi, welcome to SignalPath. In this episode, I have another interesting product review for you guys. We'll be taking a look at this Spectrum Compact Portable Spectrum Analyzer from SAF. Now, if you watched my special episode on the IMS Microwave Week Industry Trade Show, I did a little tiny introduction of this while I was there. These portable spectrum analyzers can go all the way to E-band, 86 gigahertz. They have a waveguide input. They come at several different ranges, and they're tiny, and they're essentially intended for field use where you can monitor a different kind of radiation and see exactly how much frequency is coming in, where the frequencies are, and diagnose various types of problems with transmitters directly on the field. It has a lot of really interesting features, and it's tiny. So I'm really excited to take a look at it now that I have one in the lab. Not only are we going to use it to do different experiments, we're also going to take it apart and see exactly how it works and what is the interesting engineering that's gone into it. So I'm really excited. Let's go. So let's take a look and see what different models are actually available in this Spectrum Compact, because it tells us something about how they're building these devices before we take one apart and find out. So if you scroll down here on their website, we can see the different range of models available. Now they've done what would be expected. They've basically targeted every band of wireless communication of interest, where you would be walking around and looking for a signal from either a tower or a dish or some kind of a beam-forming phased array. So they have low frequencies in the ISM band, 0.3 to 3 gigahertz. But what is really of interest to me are the millimeter wave bands. So they have a 24 to 40 gigahertz unit. That's for 28 and 39 gigahertz bands that are open for 5G. And then there is 56 and 67 gigahertz band, which is the band for Y-gig radios. And of course, 70 to 87 gig, which is an E-band radio for backhaul. So they've basically targeted these bands very carefully. And the upper bands are all waveguide connections. So the one that we have in the lab we're going to play around with is the 56 to 67 gigahertz band for Y-gig radio. Now, if you look over here, the input power range is from minus 90 to minus 40. Now, this may seem very small, the minus 40 maximum limit, before the system goes into overload, and that's because, again, this is intended for connecting wirelessly from far away and looking at a signal over the air. Or if you intend to connect it to a radio directly, you would need to do it with an attenuator. But the maximum input power is 0 dBm, so it's a little bit more difficult to damage. Now, it does have some limitations. For example, the minimum span is 1 gigahertz, and we'll see that when we are using it. But the minus 90 dBm input is extremely good, and that means that they're using a very low noise front end. So when we take it apart, we can figure that out as well. The rest looks very straightforward, and we will be more familiar with it during testing. As you go to higher frequencies, of course, you're going to have similar limitations in terms of the minimum input power and the span. But at lower frequencies, for example, 2 to 43, you will have the minimum span here is 100 megahertz, so it's 10 times better. This might have to do with the way they're detecting signal ID and the way their synthesizer works. And again, we'll find out when we look inside. But these are the different models you have. So if you're working in any of the popular bands that are coming up, this is a perfect instrument for taking on the field and doing this kind of measurement. So having said that, let's go back and take a look at it. And here's the Spectrum Compact from SAF. This is the V-band version for Y-gig radio use. And look how nice it looks. I mean, this is a complete aluminum chassis. This is solid like a brick. Very nice, fits perfectly in the hand. Gigantic screen, has no other buttons except the on and off button. Everything's handled through the GUI, which is written quite well, and we will see that. These two screws that you see here are for connecting, of course, the waveguide antenna or attenuators or any kind of a different module that you want to connect to the front of this unit. This is made in the EU, of course, and you can see the 56 to 67 gigahertz band that this one operates in. There's a tiny piece of tape that blocks the waveguide for field use so that stuff doesn't fall into it, and the attenuation of this tape must be very, very small so it doesn't really interfere with the band. And we've got places for it to be connected to some kind of a wristband, or so you can hang it up on your belt or something like those. We've got a USB port and a power port for charging. Other than that, that's all really there is to it. And everything is really well thought out for immediate field use. That's the thing I really like it. The people who design this are the people who are probably using these kind of things in the field, so they're familiar with the limitations of carrying something in your pocket and how well it needs to work and what you need to do to get it up and running. So for example, I have here the antenna for it. This is a V-band antenna. You can see it with the same connection, and attaching it to this is really quite simple, because once you pull it in, just tighten these two screws and there you go. You need no other tools other than just tightening these, and these are the things that are really well thought out in the field to get this thing up and running. But to me, one of the most impressive things for making it easy to use in the field is this. Let's turn it on. Let's go ahead and see what happens. And it's up and running. I mean, This is crazy. It's basically instantly on, and it doesn't matter. There's no hibernation mode or anything like that. It just turns on like this every time. It has a very, very fast firmware built into it, and of course the screen will adjust if you hold it differently. So I'm going to show you some of the features of the GUI, again, because it's so well thought out for field use. It's a touch screen, of course, so you can just enter whatever you want. And we're going to take a look and see how well that works. So let me readjust the camera and get a nice, good view on this, and we'll investigate the GUI a little bit. So let's go ahead and familiarize ourselves a little bit with the GUI and some of its features. And the reason I want to focus on it is because you can see why they have made the decisions they have and how easy it makes it to use in the field. So it's worth mentioning here. So first of all, I don't really like this color scheme that comes with default, so we can go ahead and change under the settings the color. I like the background to be black and the line to be completely yellow, kind of like a regular spectrum analyzer. And there it is, easy to do. On the left, we have, of course, our spectrum plot. Right now it's in full span, with the center being at 61.5 gigahertz. And on the right, you have all the buttons that you would traditionally have from a spectrum analyzer, adjusting things like frequency, span, markers, and power measurements, and so on. So let's go ahead and try to change the frequency. So as soon as you change the click on the frequency, you can see that we have red and green buttons. The red buttons are invalid, so you won't be able to press them. And this is really useful in the field when you're fumbling around trying to enter something. You might be on top of a tower or a building, and there's an awkward angle. It really helps eliminate errors when you're entering numbers. This is a huge feature, and it's so useful. So let's say we want to enter 60,000, which is 60 gigahertz. So there you go, 60. There it is. You can see I still cannot press OK, even if I want to, because there's no such thing as 6,000. This cannot go down to 6 gigahertz. As soon as I enter the last one, then all the other numbers are invalid, and OK is available. There it is. Here's our span. Now we're doing 60 gigahertz as the center. I can go back and change the span now. I can do minimum span, which is again 1 gigahertz. There you go. We're looking at a 60 gigahertz center frequency and a span of 1 gigahertz. You can see in the middle, we're making a measurement of about minus 100 dBm, which is a floor right now. And looks very good. You can see right over here, this little bar tells you where you are in the full span this instrument supports. Other than that, you can go back and you can create a marker. You can move the marker around, of course, and make marker measurements, or you can just simply do a peak, which is going to continuously search for the peak of the signal. Very simple and quick to use, and you can just center it and it will stay there. You can enter the number that you want anywhere you want, and it will go exactly to that location. If you go back over here, we can change and do an in-band measurement. This is very useful if you want to compare transmitters from different directions, or if you want to find the direction in which a signal is coming from, you can continuously make a measurement in band, which is exactly what this is. You can change the band. Very simple and straightforward again. If you go back over here under trace mode, we can have normal, and right now I'm doing normal measurement, and the normal measurement is just to continuously erasing the spectrum and create a new one. If I do a max hold, I get a new line, gives me the maximum value, allows you to search for the maximum signal in a direction and save it so you can do a comparison on the trace directly. I like the cumulative measurement too. It's almost like an eye diagram, but for spectrum, and this will continuously build up different measurements that are done, and it's accumulating power in every band as it comes along. And again, you can get a nice shape of a modulation or a signal that's moving around. You can slowly build the spectrum, and there's a counter that tells you how that is. Averages are of course available, 2, 4, 8, and 16, and you can see that they specifically put the buttons for the different averages on there, as opposed to asking you to enter the number, because it's much easier on the go to do this than to try and enter how many averages you want to make. So they've really thought about this. You can change the level, of course, minimum and the maximum. I typically don't really find that to be that useful, because minus 40 is the maximum anyway, and minus 100 is about the minimum. So really keeping it in this scale for just walking around doing measurements seems to be really sufficient. You can save your traces and do things like high contrast if you like the high contrast view. And there's a lot of settings. You can save profiles and files, and you can set a mask. And the mask can be really useful if you want to reject a particular emission from a transmitter. So if you have a mask, you can easily compare it. If, for example, for technicians on the field, which may not know exactly what numbers they should be looking for, the mask is of course helpful. This mask works exactly the same way as it works with any other spectrum analyzer. Detector settings can be changed, of course, and you can record a spectrum, and it will record it in some kind of a movie, which you can then play back. Service menu doesn't really have much information in it. There's a sound and a USB mode, which I will talk about when we hook it up back to the computer. So as you can see, very easy to use, nothing unusual. Anyone can get up and running with it. So now the question is, well, how does this even work? How do you make a spectrum analyzer this small, and how have they architected the system? So I think maybe we should, before we do any measurements with it, we should take one apart and figure out exactly how it works and understand the architecture, which of course will help when we're doing our measurements. And well, check out what I have here. The people at SAF were kind enough to send me all the different boards that make up the instrument. They wanted me to talk about how it works and how the architects. Now, they've told me absolutely nothing about how the system is built. They've just sent me the boards. So we're going to try and see if we can figure out how it is actually manufactured. But this is very nice of them to send me the individual boards so we can take it apart and take a look. This kind of transparency and this kind of commitment to the customers to show you how they build their units is always a huge plus in my book, meaning that they really care about the users, because that's the only way to know how to use the instrument best, to know exactly how it is made. So this is absolutely awesome. So let's go ahead and take a look. So we have the RF millimeter wave module, and on the other side of this, we're going to have exactly the waveguide input as you saw on the unit. So this is exactly what comes out of the instrument. So we're literally looking at the input port here. And then we have the IF and the down converted module here, where we can take a look and see what they're doing with the IF signal. And of course the digital board, which is going to have the application processor, USB, and all the other things on it. So I say we start from the front end and work our way backwards and then figure out exactly how it works. It should be pretty fun. And here is the RF module, and it's really quite nice. It's completely custom made, of course, for this instrument, and we can see the back of it here. So if I look at the front, where the instrument input is, it's exactly the same waveguide input, and the screw headers and mounters that allow you to connect antennas are directly mounted onto this. And on this side, we have the interfaces. There's really nothing that interfaces aside from two coaxial inputs and one header. So everything has to go through here, power, configuration, everything. So let's go ahead and take it apart and see what we get. There we go. So let's look at this one. Nothing unusual over here. Some gaskets to hug and shield and protect anything from being able to get in and out of the module around the coax. And then this is the empty spot, of course, for the connector. Some cavities being cut out. This over here, this tiny opening, is the back of the waveguide once it's gone through the PCB, and we'll see that there's a nice cutout for that. So there's some really precision engineering going on to machine this because it's WR15, such tiny dimensions. So, and here's the board. And take a look at it. It is absolutely beautiful, very nice, custom made, and we can start to analyze it and see what we can get. So obviously we're going to have the waveguide to coax converter. This is a very common technique to do this, where you have a back grounded piece and you create a conversion from the field going into the waveguide into a coaxial converter, and you can see nice ground stitching around that. The dimensions here are too small to machine this piece out, but you can actually machine the PCB material out so that you have better conversion and lower loss, because that's just going to contribute to dielectric losses. But you have no choice in this case because it's so small. And then there is a custom RFIC which is connected directly to the coax converter. There's a little bit of a matching network built into the PCB there, and everything here is wire bonded. And so you can, of course, wire bond at any frequency. If you can calibrate things and if you can live with some variation, then you can really do it. Even the 110 gigahertz oscilloscope from Keysight that I took apart, the front end of that was also wire bonded. It was ribbon bonded, but nonetheless, it was done the same way. Now, this RFIC over here is most likely in silicon germanium. I looked at it a little bit under the microscope, and I don't want to go into too much detail, really digging in, reverse engineering these things. I don't think that's very nice to the company, but it's most likely an a V-band down convert receiver. Maybe it's from a different product or a different purpose. They're repurposing it for this, which would be very clever. It's possible. Now, on the left side, we're going to have the LO input, and if you look carefully, the LO is differential. It's nice to be able to put a differential LO into this IC, and this is most likely because there's a multiplier inside the IC, or there is a subharmonic conversion in the IC. And if there's a multiplier or a harmonic conversion, differential is always useful, which means that this is our LO port. So the LO comes over here. There's some stubs here for filtering and so on, and then we have a single-ended to differential passive balun here with termination resistor over here, and then we go over this, and then we got the differential signal directly onto the RFIC. Everything else here is coming in and out, or just DC going on this side. Now, if you look over here, we have 4 lines that are exactly the same coming out. This leads me to believe that this is possibly an IQ down converter. It may be that they just have 2 outputs, but I think it might be an IQ down converter, which leads me to think maybe this chipset is used for some other radios and they're using it for this purpose here. Now, they're doing 2 things with it. They're taking one of them and they're tapping on the side, and they're going single-ended through this balun, and they come out of this, which means this is a higher frequency output. And then on the other side, the other 4 terminals that just get buried deep into the board, and they come out on this side, which means that they're capturing one side of the down converter at a high frequency and the other side at a low frequency. So they're doing something interesting and unusual with those 2. Now the question is, where does this IF and this IF actually go, and how do they treat it afterwards? So for this one, everything kind of makes sense. So some low frequency LO comes in because differential probably gets multiplied, RF comes in directly, and the IF comes out at two different frequencies, two different filter bands, a low frequency and a high frequency. So let's follow these signals onto the IF board and see what is happening to them. And here is the IF board, and we can go ahead and track all the signals we just talked about. So for instance, we have the LO signal over here, the IF coming back here, and the low frequency IF coming back here. So we can go ahead and find out how they're generated. So the interesting one to start is, of course, the LO. Now, if you look at the LO, it's all generated underneath this cage here, and it's a really straightforward architecture. We have a Hittite VCO, we have a divide by 4, we have a Hittite power amplifier here, this is up to 20 gigahertz, we have a VCO from up to 18 gigahertz or so, a divide by 4, and a PLL synthesizer. So the combination is going to give you frequencies of up to about 15, 16 gigahertz, which means that this is an LO in quarter rate, so it's 1/4 of the RF frequency. And this means this even leads more to us thinking that there is a quadrupler on the RFIC I just showed you in the front end of the unit to create the necessary LO frequency to be in line with the frequency that's coming into the unit. So the LO synthesizer portion is really quite straightforward. The IF is a little bit more interesting. The IF signal coming in is going to, on this side, it's going over there, it goes into this board on the other side, and it is processed by some amplifiers, and then interestingly enough, it goes into what appears to be a SAW filter. And then after the SAW filter, it goes into a logarithmic power detector, also from analog devices. And this logarithmic power divider has like 90 dB of dynamic range or 80 dB of dynamic range, and it's supposed to work up to 4 gigahertz. So the high frequency IF goes into a logarithmic detector, 80 dB dynamic range up to 4 gigahertz, but there's a SAW filter, and I couldn't find information about this, so obviously they're not using the entire frequency range of this. So they have a power detector, that makes sense, you would need that, but then what are they doing with the low frequency one? The low frequency signal goes over here, enters the unit from here, is filtered very carefully with LC filters, and then goes into an op-amp, a differential amplifier, filters some more, and it goes into another logarithmic detector. This one is only up to 440 megahertz, and this has 95 dB of dynamic range. So it's interesting what they're actually doing. They're doing a logarithmic detector at low frequencies and a logarithmic detector at high frequencies, taking potentially the I and Q signals of a down converter RFIC. Now, I don't know exactly why they're doing that, but my guess would be that they're using that to be able to do signal ID detection, so they can distinguish the image from the real signal by moving the LO around and looking at the power detected in the two power detectors, and in the way in which they change as you change the LO frequency back and forth, you might be able to tell the direction in which the image is moving, and then therefore you can tell where the actual power is and remove the image from it. That's my guess. Maybe they're doing something else, but I think that sounds like a reasonable idea that might be what is going on. But other than that, a simple low-cost architecture using obviously good components to be able to accomplish what they're doing, be able to build a very high frequency down converter with very good dynamic range for this type of applications. So now let's move on to the digital board to complete the teardown. And the digital board is really straightforward. Aside from DC-DC converters, USB hosts, and some kind of charging circuitry, we have an SDRM processor, very fast memory next to it. We have room for a micro SD card, which is most likely populated in the actual unit. That's where the firmware and all the files are. And in fact, when you connect this to the PC, it will mount itself as a drive. That's really beneficial because you can get manuals in and out of it and files in and out of it very easily. So that's definitely what is going on there. On the other side, we have absolutely nothing. It's just everything is on this side. So really nice and simple architecture. There's a ribbon cable from here, which connects to the IF board, and this ribbon cable over here is most likely going just to the display to give all the information back and forth. So really quite straightforward architecture. All the magic, of course, is happening in the front end, which I talked about, and of course in the IF board and how they interact with each other. Nice architecture. So now that we know this, we can go back, do some testing, and see how it behaves. So let's go ahead and use this instrument to analyze some signals which we don't fully understand the nature of. So here in the background of the lab, I'm generating some signal, some mystery signal, and we are wirelessly looking at it with the spectrum analyzer. So obviously behind the spectrum analyzer, there's nothing. So this is all wireless link. So let's go ahead and zoom in here so we can see what we get. There is a screen over here. And if you look carefully, you can see that our signal is around here, but it's jumping around. So every time we have a sweep, the sweep takes quite a bit of time. So therefore, the signal is going to appear in a different location. Sometimes it's small, sometimes it's big, and it's going to be all over the place. Well, one way for us to figure out where to look is obviously to do a marker. So if we do a peak marker, there it is. Now our peak marker, you can see, is going to jump around, and the frequency is going to be reported here at the top right. So it looks like it's sitting somewhere around 60 gigahertz. So it would make sense to focus in that area and expand our span and see what is going on in that region. And that can be done very easily. We go back, we go to the frequency, and we set our center frequency here to be 60,000 megahertz, which is 60 gigahertz. There it is, and we can go back and change our span to be minimum span. Now the signal looks a lot more interesting. We can see that it is jumping around, and indeed it seems to be confined within this 1 gigahertz band centered around 60 gigahertz, and the peak is obviously continuously tracking it, and it looks like it's moving from the right side of the screen to the left side of the screen, but the amplitude isn't the same all the time. So it would be nice to get an idea about the amplitude distribution of the signal. Now we can see that it's moving around. Now there are sweep over here has a certain speed. Unfortunately, it doesn't say what the sweep rate here is in time. But again, this is part of the specification. You can find out how long it takes for it to sweep, and then you can figure out how fast the signal is sweeping. But the more important thing is to take a look at the distribution. So if I go to the trace mode and I do a max hold, and I can just wait a little bit, and the signal is going to slowly build. And we can already see some interesting characteristics of the signal. First of all, we see that it has a peak at around 60 gigahertz, and the signal symmetrically falls down on both sides around 60 gig, and it is confined within this 1 gigahertz band that we're looking at. So that's already pretty useful. It tells us where the signal is and its behavior across time. So we can go cumulative, and it's going to give you some statistical distribution in exactly the same way. Sometimes this can be more useful as the signal is changing and jumping all over the place, and you want to get an idea of how the distribution of the signal is building over time, which we can see over here. If I wait long enough, I will of course get a similar screen again. So here I waited a little bit longer, and you can see the distribution of the signal being built here, but it's very clear that the signal has more statistical presence at the peak rather than the amplitude. This tells me that the signal's essentially always at the constant amplitude, and all the points we see captured in the middle are the result of the sweep itself. So this already gives us additional information where the max hold may not be giving you, because of the fact that this is literally a statistical build of the signal itself. So now we can go back and we can change the trace mode and put it back to normal. And then what I can also do is I can go back and do a band power, and I can look and see what kind of numbers I hit whenever the signal is in this band. Now, this is going to be a difficult measurement to make because you don't know how much of the power is captured within that band. Of course, that's going to always be the case. But I can increase the band. I can change the band to be 1 gigahertz, like so. Now it's the full band, so every time I see a tone, I'm going to be able to measure the power of that tone. And if you look around, you can see that we hit numbers as large as minus 50 dBm occasionally, but because the signal is moving around, it's going to make that measurement difficult. But if I have control of the transmitter, I can change that. So let's go back to 250 megahertz here, like so. And then we have the signal jumping around. I can go to the transmitter and change the transmitter and put a tone right in the middle so we can get the amplitude of the tone as well. And here we are. So I now settled the transmitter at a 60 gigahertz continuous tone, and you can see the power is about minus 53 dBm or so, which was the maximum we were seeing occasionally when the signal was sweeping. And if I put my hand in front of it, you can see the signal will go through because 60 gigahertz is going to be completely blocked by my hand. Of course, it has a very shallow skin depth absorbed by water very easily in my hand. So you can see that we can make this type of in-band power measurement quite easily. In cases where you have control over the transmitter's sweep time, you can make a very nice over-the-air measurement of the power distribution of the transmitter, which is what I'm doing in this case. So if I go back over here, and if I go and turn the in-band power off, and if I go to the trace and enable max hold again, we can see we can build very easily that transfer function. Now, we could do this even when the transmitter was changing very quickly, but this is a much nicer way of getting immediate result if you have control over the transmitter. And this can be very handy in situations where you want to know at a certain distance whether you have the particular power range you're looking for. Now, one of the biggest advantages of being able to walk around with a transmitter like this is that you can catch multipath and see fading under some circumstances. Now, multipath is pretty difficult to emulate. You have to have proper reflectors around, but of course in the field, if you're unlucky, you're going to be able to hit that condition fairly easily. There you go. Now that we have had it built for a while, you can see a very, very nice plot of exactly where the signal spends most of its time, which is what I was trying to measure initially. And you can see we have a very interesting response. This transmitter is clearly tuned at 60 gigahertz. It has the highest power coming at 60 gigahertz. The distance between this antenna to the transmitter is not very high, and therefore these drops that you see here are simply the transfer function of our transmitter itself and not from over-the-air measurement or from anything else. That's pretty interesting. Now, there are of course limitations. In this particular case, we have a signal jumping around so fast that the instrument doesn't have enough time to accumulate enough energy to be able to show you the correct amplitude at any given time. This is of course the limitation of having only 1 gigahertz as being the minimum sweep and having the sweep being at the rate it is. But of course, in an instrument that's low cost at these frequency ranges, this is to be expected. For most applications where you have a modulation and you have an average power distribution over time, this is not going to be an issue. So in this case, where the signal is sweeping very fast, if I go to trace mode and I go at max hold, I'm going to have to wait quite a bit of time in order to get a proper distribution. And as you can see, initially the shape of it doesn't look quite right. That's normal, that's to be expected. It's not necessarily a weakness of the instrument, but there are some scenarios where you will not be able to get what you're looking for. But in this case, I get some additional information which would otherwise be invisible. So for example, in our sweep, this tells me that even though the sweep is very fast, the instrument spends most of its time at the beginning and the end of the sweep. This measurement is actually really hard to do because you don't have any way of knowing how long the instrument spends at a particular frequency. But because statistically it spends more time at the ends, you can see that the instrument catches that and tells you that there is a dwell time at the beginning and end of the sweep of my transmitter. That's actually something I didn't know about this until I used this instrument. So there are some valuable information you can extract from the behavior of the unit. And what about trying to look at a signal from an actual product that's on the market operating in WiGig? This is a DVDO Air. This is a 4K over-the-air transmitter. It transmits uncompressed HDMI signals on a 60 gigahertz carrier using the SiBeam's phased array. Now, I'm going to do a full teardown and explanation of how this works at a later time, but the only thing you need to know that this does have a phased array operating at 60 gigahertz, and of course the band is exactly the band of frequencies that this spectrum analyzer works at. So now that I have a link between this and my TV, I should be able to point my receiver there, point the spectrum analyzer in this direction and see what kind of spectrum is coming out of this and see if we can extract any interesting information from the way this is behaving. Now, if you didn't have the spectrum analyzer and you were walking around, it'd be very hard to know if this is even working if you had a problem with the link, because it's very difficult to capture 60 gigahertz signal coming out of this. But of course we can do that with the Spectrum Compact. Okay, again I have the receiver directly in front of the SiBeam 60 gig transmitter here. So let's go ahead and turn off the SiBeam transmitter so we can see the baseline of the spectrum. I'm going to zoom in here. There it is. I'm going to plug in the transmitter, and now you're going to see exactly the sequence of handshaking that goes between the transmitter and receiver during initial power on. So during the initial power on, the transmitter is going to put out a lot of power in different bands in order to be able to find the receiver. And once the handshaking is established and the signal actually goes across and a link is created, we can see then it starts just flooding the spectrum, jumping all over the place, getting all the different bands sorted out. Now 60 gig is a quite broad band. It's channelized and it's going to jump back and forth trying to find the best link. But if I do a minimum span here, you can see some interesting characteristic, and it looks like occasionally these peaks that you see are most likely for synchronization. So there's a beacon that it sends out so it can find out which beam is the right beam, and then there's a burst of activity which is the actual packets being sent, and you can see the power goes up and down. So the power went all the way down, and the reason for that is because it found the path between the transmit and receive that required the minimum amount of power. So now it's established that path and it's going to stick with it. And the only way the power is going to go back up again is if the links is disturbed. So this kind of behavior of transmitters that are dynamic can still be captured with the Spectrum Compact. You just have to play around a little bit with it more to get the behavior. But it's very clear that it is doing exactly that. And if I go back to full span, you can see now the spectrum is going to be, not as high because of the fact that the power from the transmitter was reduced. So even though you can't get in detail information, you can get the direction of the signal, you can get any kind of fading, any kind of synchronization. There's a big tone right there for alignment. And you can get that information out of the unit itself. So on the field and on the go, it's pretty useful. So one of the other nice features of the unit, it has a very good user interface for the PC. So once you connect it to the USB port, it establishes a communication port, and then it directly communicates with the GUI over the COM port. Then you can see the spectrum and do everything you can do, and in some cases even more on the GUI than you can do on the unit itself. So here we have a tone. We can clearly see the tone here, and I want to look at it. Well, there's a couple of things I can do. I can put a marker on it. Here's marker 1. I can do a maximal. There you go. It measures that, minus 58 dBm. Looks very nice. I can go ahead and change the frequency to center it exactly like I would, except that here I actually have 60 gigahertz button. There's a gigahertz button here. So you go to span change, it moves in the middle, and I can change the span from 8 gigahertz, let's say, to 2 gigahertz. And I should be able to see the tone. There it is, nice tone in the middle. But I think I may have found an unusual bug here. If I change this from 2 gigahertz to 1 gigahertz, you can see that the signal disappears. I wonder why. Now this doesn't happen on the unit itself. On the unit, I actually see the tone. It just doesn't seem to show up here. Something must be weird going on between the GUI interface to the user, to the machine, and to the PC itself. A little bit weird. Let me see what happens if I change this. Can I change this? No, I cannot change the divisions. So yeah, it's a little bit unusual. It might be a minor bug. I'm sure they can fix it. If I go back to 2 gigahertz, it shows up right away. So the GUI is nice, gives you lots of features. You can record things, you can take screenshots, and you can actually mount the unit as a drive and then put files in it and remove the files from it. That is very useful because the unit itself actually acts as a storage unit. So you have basically a memory card in your pocket as well as the unit itself, and you can put files in and out of it very easily. So very nice little feature. I wish more instruments did this, especially portable ones. And there you have it. I hope you enjoyed this full review of the Spectrum Compact product from SAF. I will probably be getting the lower frequency version of this as well, the 24 to 40 gigahertz one, so we can do even more experiments once we have the other one and take a look at some of the other impairments transmitters in the field can experience, like multipath and other nonlinearities and so on. So it should be very interesting to try and play around with the other module when it comes available. In the meanwhile, I hope you like this. If you do happen to purchase one of these because you saw my video, if you did enjoy this video and you want to let SAF know about that, please do so. I get no return on any of the sales, of course. This is just so that I can continue to have a good relationship with the vendors. And this would allow me to bring more of these kind of products and take them apart and show you what's going on inside them. So I hope you like that. I'll see you in the comment section.